topic is the one that was moving on from potential dividers. So it's best to look at potential dividers first. However, this one we're dealing with is called internal resistance. Now let me just present to you with the problem, or the manifestation of internal resistance. In essence, if we start with a battery, just any type of battery, and we put it across a resistor, then what we have here is obviously a current flows, and we can measure a potential difference across that resistor. Now let's imagine this is, say, a 1.5 volt cell. Then what we're expecting is 1.5 volts, a coulomb. It comes out and with 1.5 joules on each coulomb, comes around and deposits all of its energy into the resistor, and so therefore we're expecting about 1.5 volts appearing across that resistor. However, that's not always the case. The potential difference that we're getting between these 2 points here, potential difference, is always less than or equal to, in some cases, the 1.5 volts. So that means to say that some of the energy, these coulombs coming around, has been used elsewhere and lost, and the remainder has been put across the resistor. Now, the reason why it is less than or equal to is because inside the structure of the battery, there is some resistance. So when you make up the battery, I mean, you don't add a resistor in, but the very makeup of a battery presents a resistance. So what happens there is we label that, we say, rather than trying to describe where it comes from, we just say, well, that's like having a resistor in series with the rest of the circuit. And so if this is our battery here with the positive end, so I'm trying to dot an outline of a battery, then we can say inside this somewhere in its internal makeup we have a certain resistance which acts as if it's in series with the rest of the circuit, and the rest of the circuit with an external resistor. So we call R the internal resistance. And it just means that not all of our voltage, or the energy per coulomb, will be used up over here. Some of it will be used up over this resistor, and so therefore what I want you to bear in mind, and keep bearing in mind, is our idea of our potential dividers. We could redraw that circuit if you like, and I'll just draw it small here, as the battery, the resistor itself, a small resistor in series with it, and therefore potential is shared. Some is shared across here, and the remainder is shared across there. Good, so sort of keep that in mind, your potential dividers. Okay, good. So in effect, let's use some terms here. The potential difference is really important this time, because now it's telling you how much is being deposited over the resistor. This 1.5 volts that I mentioned before, the 1.5 volts is known as the EMF, or the electromotive force. And that means, if we need to define it, it's the voltage provided when no current flows. Okay, good. When current flows, of course, then the larger the current, the more volts that will be lost from this bit. Let's call them volts lost from there. So I suppose what we can say here is we can start building up our equation, and we can say to ourselves, well, the EMF of the battery, the total electromotive force, is going to be shared between the potential difference and the volts that are lost out of the circuit that we can't make use of. If you prefer, we could write this equation as the EMF is the potential difference minus the current that's flowing multiplied by the internal resistance. the bigger the current, the bigger this factor is, the number of volts lost, therefore the smaller the reduced value that you draw over your resistor and can make effective use out of. So I suppose what we need to do is we need to look at how these two compare. So what I think I'll do first is I'm going to show you what would happen if this is our total EMF that's provided. Let's say this is our value for our EMF. Then if I have a very small current flowing, so this is a small I, then what happens is the majority of that EMF is being used as the potential difference, and a small amount of it here is the lost volts. Yep. Now, as we increase the current, let's take it to the next level. Now, this is the PD, because now a larger quantity of it is being lost. And if I continue to increase the current, the PD available is reduced, because now we have a much bigger amount of the volts lost. And so this can continue. PD, and now we have a significant amount of lost volts because the current is becoming significant. I is large here. So you see that share. So now, if I were to have a large current flowing, large currents flowing here, then I have a significantly reduced PDF. And when we do an experiment, we vary the resistance here, thereby varying the current, thereby being able to achieve a range of currents. And what we get is, if I were to plot now the potential difference in volts against the current in amps, what I get is these significant points here. And I continue to get them, which gives me a line of best fit that looks like that. What it's saying is, of course, you've lost some, you've lost more, you're losing even more because the current's getting bigger and bigger and bigger. And as the current gets bigger and bigger and bigger, so the lost volts gets bigger and bigger and bigger. We've seen this experiment, you've drawn that graph, you've got that graph out. But what you need to be able to interpret from that graph is, first of all, the y-intercept is equal to the EMF. Hopefully as well you'll remember that the gradient is equal to the internal resistance. And why is that? Well, not only because of the theory that I've explained to you, but if we know that the equation of the straight line is y equals mx plus c, I've plotted my potential difference on my y-axis. So I'm moving my potential, leave my potential difference there. That should be a plus sign there, sorry. So I'm going to leave my potential difference there, and I'm going to move this onto the other side. So I'm left with EMF plus minus IR. Y is my potential difference. My X is my current. So I'll plot my current there. The gradient is the internal resistance, and the y-intercept is my EMF. Good, I hope that makes sense. In essence, if you can understand the idea that the voltage is just being shared between the two resistors, one internally and one externally, and depending on the current, depends on how much that share happens, will be okay to do the questions. So here come some of the questions. Okay, right, we'll start with a nice easy one. We'll set up the question as we're familiar with it. Nice internal resistance. Here is my big battery. Sorry, my cell. It's a big battery, but nonetheless we'll draw it as one. And coming out, we're going to put it across 10 ohms. I've got an EMF of 2.5 volts and an internal resistance of 0.2 ohms. Now, first question is, what's the current that's being drawn? And therefore, what's my potential difference over the 10 ohm resistor? Okay, if you think you know, hit pause, give it a go. So here comes the answers. Okay, first of all, the current. Well, the current is the EMF divided by the resistance, the total resistance, which is the same as saying divided by R plus little r. In other words, these two are in series. So just like the potential divider, we're doing exactly the same potential divider here. That gives me, well, 2.5 over 10 plus 0.2. And that gives me 10 over 10.2. It's subtle. These are very small differences, but they're important. If we hold on to the 2.5 divided by 10.2, it gives me 0.245. 0.245 amps is the current that's flowing through the circuit. Okay, so the second one is, what's the potential difference? Sure, you can see this is just like the potential divider equation now. Well, now let's look at our equation that we're saying. The EMF minus the internal current times the internal resistance gives me my potential difference. So substitute that in 2.5 minus 0.245 times 0.2 gives me 2.45 volts. So this is what can be achieved there. However, we could also say, and we could do it via the potential divider method if you like. I'm just going to put this in brackets, potential divider. And we said that the potential difference is going to be the voltage in divided by the total resistance multiplied by the resistance which you're working over. Let's say that's R2. And let's just put in the numbers just to make sure that works. So the potential difference, we're unsure of, 2.5 divided by 10 plus 0.2 multiplied by 10 gives us, well, that's exactly what we've done here in effect. Let's just make sure that works. .45, yes it does. Thank goodness. So it's whichever way you want to do it, really. I mean, there's two ways of looking at this. You either look at it in terms of the internal resistance equation, or the potential divider. Second example, let's imagine we take exactly the same setup, but this time we put it across a 1 ohm resistor. 2.5 volts, 0.2 ohms. First question, current. Second question, potential difference. What do you think they are? Why don't you hit pause and then give it a go and check your answer with this. The current, first of all. Well, this time it's significantly larger because we have our total resistance is now only 1 plus 0.2. So we have a significantly larger current, and hopefully we will realise that. So we have 2.083 amps, that's huge. Now hopefully, go back here, you can see that when we're using a significantly higher current, the potential difference available to us is more because greater amounts are lost. Let's see if that's the case. So potential difference is now the EMF minus the IR. Let's go with this method. 2.5 minus our current multiplied by internal resistance, giving us, well, that's significant. So all that we've got left is 4.16 volts. A tiny amount. Good. Okay then. Right. Here goes with another couple which are a bit trickier. So hopefully we'll be okay with this. We're going to look at a battery that we throw across a voltmeter just directly. Now this voltmeter is a 10 mega ohm voltmeter, and it registers 1.3 volts across this battery. Now if we put the cell across a 20 ohm resistance, then we put in the voltmeter reads 1.25 volts. So why is there suddenly a difference going on here? Let me describe it first and then I'll let you sort it out yourselves. 10 mega ohms is nearly infinity ohms, or we can assume it's infinity ohms. And that means that no current is drawn. In actual fact as well, if you bear this in mind, if you had a 10 megohm in parallel with a 20 ohm, then the total resistance, I hope you can recall this, is going to be the multiplication of the two divided by the addition of the two. And when you plug that into your calculator, you just get 10 megohms back. Sorry, what am I talking about? You just get the 20 ohms back. So with a huge resistance like this, you can almost ignore it from the system. It's drawing no current, so it's having no effect upon the circuit. So what you're measuring here is the EMF. Now, with that in mind, can you work out the internal resistance of that cell? Hit pause, otherwise here comes the answer. Okay, EMF minus IR gives you the PD. We can say our PD is 1.25, of course. Our EMF is 1.3 minus IR. IR is the difference, 0.05 volts. R is going to be 0.05 divided by the current. The current is the EMF over the resistance, which gives us 1.3 divided by 20, and that gives rise to 0.065 amps. .77 ohms. Good. Just one more, a little bit more complicated to make life fun. Here is a circuit which has two resistors in it. There's an internal resistance in our battery, we know the drill. Now, if we put them in series with each other, it draws a current of 0.75 amps. If we put them in parallel to each other, then that draws a current of 2 amps. What is the internal resistance? And what is the EMF? Okay, see how you get on with that. And here comes the answer. Okay, in the first instance, you know the EMF is equal to the PD multiplied plus the current times internal resistance. Or you could say to yourself that that's actually the current times the bigger resistance, the total resistance, plus IR, which is the same thing, EIR plus R. Good. It's the same with this one as well. So you can say to yourself that the EMF must be the same in both. So therefore the first current by the first resistance must be the same as the second current by the second resistance. Right, what does that present? That is simple, it's a 10 ohm, and we've got that current. What do two 1.5s present? Well, 2 of equal measure presents a half. So we have 0.75, 10 plus little r, gives us 2, 2.5 plus r. Do a bit of jigging around and rearranging, means that R gives us 2 ohms. Okay, substitute back into this one here. 10, well, 0.75, but it's 2, that's 12 by 0.75. That is obviously equal to the EMF, so the EMF is going to be 9 volts. Good, a little bit more complicated there, but I hope that makes sense, and that should be the topic covered.